Hello everyone. Today I want, since I found my um, last Friday's recording disappeared, and I just want to upload this video to help you understand how to do this level 4 and to help you understand what you need to do. Yeah. Okay, so in this class is for the continuous time filter design and analysis, and you will learn how to design a filter to help remove the um, some parts of some parts in this music piece. This music piece contains the drum part and the flute part, and we hope you can remove the remove part. So the remaining part is only the drum part. Yeah. So firstly, in the part one, you need to know how to design our no, it's not how to design. It's about how to experience um, the how to experience the system response uh, based on uh, based on a particular circuit. So suppose that this is the operational amplifier circuit. So firstly, we need to transform it in the block diagram presentation. And so I just draw this figure, and you can see this part has been transformed into this part, and this part is transformed into this part. So based on the cascaded system rule, and if two individual system is cascaded, the combined system response should be the multiplication of these two individual system response. So which means it's the inverse of Z2 omega times minus Z1 omega. You can see the final representation should be this. So according to this example, we can see since Z1 omega is the function of j omega, and Z2 omega is also a function of j omega. So and so our system response general form should be like this. Should be looks like this. Yeah, you can see for both for both the numerator part and the denominator part, both of them are the function of the j omega. But what we need to know is the coefficients for the numerator, coefficients for the denominator, and how to how to calculate this coefficients is very important to design. Oh, no. How to calculate this coefficients from based on the circuit is what we need to learn today. So you can see, suppose that we have already know the coefficients for the numerator and the denominator. They are for example, in this case, they are the coefficient vector b1 to bn, and this is coefficient vector a1 to am. Suppose that we already know that we already know this coefficients vector. How we use our built-in function to show the system response. And this part will tell you how to show the magnitude response of this system and the phase response of this system. And you can see, and you can see this built-in function is what we should use. And this numerator corresponding to the coefficient. This numerator is a vector that's corresponding to the coefficient vector b1 to bn, and this denominator is coefficient. This denominator is corresponding to the coefficient vector a1 to an, and this omega is defined by ourselves. That's the range of omega. Since I mean the range, the final response should if we look into the magnitude response, the y-axis is the magnitude, but for the x-axis it's the frequency. Is corresponding to the frequency. So this omega should define, and this omega is to define the range of frequency. There is omega. That's for the x-axis. So now suppose okay. So after knowing all of this, let's check one example to see how to use the MATLAB to experience the response. Suppose, in this example, this is the standard inverting operational amplifier system. Since you can see there are two resistors, R1 and R2, and you can see according to what we learned from this case, firstly we should oh, wait a moment. Sharing. Okay. Firstly, we should transform this circuit into the block diagram representation. You can see after that, this R2 is corresponding to R2 inverse of R2, and this R1 should be minus R1 xt and yt. So the final system response should be R inverse of R2 times minus R1. So it should be minus R1 and over R2. So according to this final system response, we know that for the numerator, part, it has only one value, and this one value is corresponding to that zeroth order coefficient, and for the denominator part, it has also one value. It's also corresponding to that zeroth order coefficient. So now let me show how to use MATLAB to experience the response. In this case, R1 equals this value and R2 equals this value. And now we define the numerator part. Since it has only one value, so here is only one value, it's matters R1. And this is the denominator part. It has only one value, so this is R2. So, and I have defined a frequency range by using this building function. This building function defines the frequency range is from the 10 to the 10 to the minus 1 to 10 to the 5. So that's what I have defined. So, and if you are not familiar with this this log space function, you can just use the documented system to know it. For example, okay, and then I just put the numerator vector here and denominator vector here, and put the W here, and you can see this is our final system response. And I have defined the plot frequency response function, and since it contains it just contains this part. So yeah, it will show the magnitude response, and it will also show the phase response. Okay, oh, let's just show it. Let's just output it to see what will happen. Okay, you can see. You can see I have output. I have outputted two. I have output two figures. The first one is the magnitude response. The second one is the phase response. And according to the, you can see, wait a moment, 10 to the minus 5, 10 to the minus 4. Wait a moment, let me check this part. Log space. I think it's 10 to the minus 1 to 10 to the minus 5, but the results that the MATLAB given me shows the ranges from around 10 to the 10 to the minus 2 to the 10 to the minus 4. Okay, I think that doesn't matter. You can see according to the magnitude response, there is no magnitude change. So I mean, the magnitude response is constant over all frequency, which means this circuit will not change the magnitude of input signals. But you can see according to the phase response, the phase is around 2.1, right? So which means, but it is also a constant, which means wall phase, which means since if if this singles have different has multiple frequency parts, for all frequency parts, they will be changed. They will be wait a moment. They will be changed, and the phase will be changed to the same level. Oh, the phase will be changed by the same level, which means the phase in this case. Yeah, I think the phase will be changed by the same level. So yeah, that's the phase response. Okay. So now let's look into another example. This example, it's a integrator system. You can see it contains two different parts. One is the resistors, and the second is the capacitor. Okay, so what we need to do is to transform this circuit into the block diagram representation, to see how we can use the general form to explain this circuit. So the first part is transformed into this part, and the second part is transformed into this part. Then we can see the final H should be -1 over J omega R4 C3. So according to this equation, we know that for the numerator part, it has only one value, and this value is -1. It's corresponding to the zeros order coefficient. And for the denominator part, it has also only one value, and it's correct, but it's corresponding to the first order coefficient. So now what we need to do is to define this equation in our MATLAB. Okay, so you can see here I have defined the capacitor and the resistor, and they are the C3 and the R4, and corresponding our equation, this one, our numerator has only one value. Our numerator has only one value. That's -1 is corresponding to zeros order coefficient. But our denominator has one value and has only one value, but it's corresponding to the first order coefficient. So this is our first order coefficient, but since this is a vector, so we still need to define its zeros order coefficient. But since the zeros order coefficient is 0, so we just put 0 here, which means the there's order coefficient is just 0. Okay. So if you don't put 0 here, this equation just tell us this equation just tells us for the denominator, the zeroth order coefficient is C3 times R4. So we must add 0 here to make sure that there are two coefficients. And the first is C3 times R4, and the zeroth order coefficient is 0. So yeah, then I still use the built-in function to show the response. You can see it will be like this. Okay. Dun -dun. You can see the magnitude has changed over different frequencies, but the phase didn't change. Didn't change. Yeah. Okay. Now let's check. Let's look into another system. This one. Yeah. If you actually we still can separate it into two parts. One is the resistor, and the second is this part. It contains one capacitor and one resistor. And you can see if we transform them into block diagram representation. This one should be this, that one should be this, and then the final H should be the multiplication of these two individual systems. So this is the final equation. You can see for the denominator or for the numerator part, it has only one value. And it's corresponding to the zeroth order coefficient. But for the denominator part, it has two values. The first value, it has two values which corresponding to first and zeroth order coefficients. R8 is corresponding to zeroth order coefficients, and R7 times C7 and times R8, that's corresponding to the first order coefficient. So now let's define it in MATLAB. Okay. I have defined C7, R7, R8, and the denominator, the zeroth order coefficient is minus R7, and for the denominator, the zeroth order coefficient is R8, and the first order coefficient is R8, R7, C7. So the final, so the final response should be like this. Yeah, you can see at this range, the magnitude response doesn't change. But at this range, you can see the magnitude decrease in this range. Yeah. And you can see, you can also see, let's see, the phase changed across the different frequency. Okay, now okay, now what we need to do? Okay, Okay, so the summation system and the cascaded system is the system rule of how to combine um, individual systems into a complex system, and to make you know how to get the final system response. So you can check this part by yourself. Yeah. Okay. Next, I want to say is the feedback system. To define a feedback system, we need to know how to get the system response. So yeah, here we have H1 of omega and H2 of omega, but interestingly, there is a feedback loop. There is a feedback loop. So by we need to find the system response of this feedback system. So we need to do first. We need to use this equation. Since suppose since y of t is corresponding to y of omega, so this is y omega. We can see if we follow this branch, it should be equals to x of omega times h1 of omega, and the plus. Why this plus? Since we will follow this branch, and to this way, you can see here is y omega. So y of omega times h2 omega, and then times h1 omega. So if we just move this part into this if we move this part to here, and you can I just change the order and then do some calculation, we can see our final system response will be like this. Yeah, will be like this. Okay. Oh, so yeah. So after learning all of the basic rules, uh, of systems, and the summation of system, the cascading system, systems, the bi-quad filter system is the application of all these rules, and you can see what you to analyze this system. What you need to do is first separate this complex system into different individual systems. I mean, separate this complex system into distinctly different individual systems. Here, I just divide. You can see it, and this complex system can be divided into five individual systems. This is H1, this is H2, this is H3, and this is H4, and this is H5. And we have also the feedback loop. So here I have help you to define this. I have helped you define these individual systems here, and if you follow the feedback system rule, you can find our final system response should be like this. And then if you replace this individual system response with this equation, finally you can get the correct answer, the final system response. And I think the lab we have already give you this equation here. So what you need to do, if you are interested in how to calculate the complex systems response, and you can follow this steps to compute it. But if you are not interested in it, you can just use this equation to get the response. Okay. So now, let me show you how to define the biquad filter system in MATLAB. Okay, so here I just follow this instructions. I just define the hyper parameters k, omega c square, q, a, and then I define the numerator vector and the denominator vector here, and you can see our biquad filter will look like this. Dun, dun. So okay, so this is our this is our this is our biquad filter system. Yeah, you can see here I define here. Let me see. Is around. Here there is a definition of cutoff frequency. The cutoff frequency here is around 64 Hertz. Cutoff frequency is corresponding to when the magnitude decreases to about -3 dB. Oh, I mean, I think I can't explain the cutoff frequency very well, but if you Google it, I think you can get the correct answer. Yeah, just Google it. Okay. Okay. Now, the final part of the part 1 is the cascading two biquad filter. To biquad filter, since we already know if we cascade two filters, the final system response should be the multiplication of these two individual systems. So here, oh my god, yeah, it's a little complex since for each biquad filters we have for example this expression, and for the second biquad we have this expression. Then what we need to do is to calculate the this combined system's response, which which means we need to compute the final numerator coefficient vector and this denominator coefficient vector. I think I have helped you to define it in this way. You can see for the combined two biquad filters, the numerator, the numerator part is Z1 times Z2, and the denominator part is this. Okay, yeah. What I can do is just give you this equation to help you to define the two biquad filters in MATLAB. Okay, so this is the one biquad filter, and this is two biquad filter. Yeah, this is the final equation. This is final equation. Then this is totally corresponding to this equation. These two equations. If you check my part here, and I think you can do it by yourself. Yeah. Okay. Now, what we need to do is the second part. Wait a moment. What we need to do is the second part, which is the design low pass filter. Here, and in this part, for the low pass filter, we will use this two biquad filters, and since we will use this to replace, not replace, to remove the flute part. Okay, wait a moment, let me see. Okay, I can share the sound now. So let me show the music piece. Let's listen to the music piece. Oh, sorry, I'm a little tired. Yeah. So in this music piece, we have two, I think, two parts. One is the drum part, and one is the flute part. And you can see the flute part is corresponding to high pitch sound. So which means the frequency should be high. But the drum is corresponding to the low pitch sound, which means the frequency is low. So what we need to do is remove this part, and the remaining part is only this one. Okay, so what you need to do? Yeah, if you remember, we have defined the two quad system, and it the magnitude response looks like this. So if so you can see at this range of frequencies, the magnitude is constant. But for the but for this range, the magnitude decreases to a certain level, which means so what we need to do? The ideal filter should remove the ideal filter should maintain this part and remove this part. But generally, we can't have an ideal filter in reality. What we need to do is define a filter have the similar shape, but we want to this. I mean, yeah. Ideally, we can. Oh, I don't know how to say. Ideally, we want to. There is a straight cut here, but we can't do that. So this is if we define here as our cutoff frequency, and the corresponding level is minus 3 dB. There is 0. This is cutoff. So we can have yeah, just remember. So this is very similar to our 2 by quad filter. So what we need to do is to find the cutoff frequency and then define the to define the 2 by quad filter, and then use that filter to use that filter to filter with the music piece to remove that flute part. So I can show you how to. So I can show you the final result if I just use my self-defined by quad 2. If I just use my self-defined filter. Okay. So this is the original frequency representation. Yeah. And if so here I have defined my filter. I have defined my filter numerator part and the denominator part here, and this is they are coming from the 2 by quad filters. So okay. Yeah, you can listen to this music. Right now, you can see there is I think there's no flute part, right? But it's not so perfect. It's not so perfect. But you can see according to the filtered frequency representation, you can see there only contains some low frequency range. So this is my filter here. You can see, suppose if we check the minus 3 dB part, I don't know. it's all about the hair. I don't know. Since I just follow the cascading two bi-quad filters and to design my filter, and then in this level they have told us the cutoff frequency is around 300 hertz. So what you need to do is to use this information to design your filter and then remove that flute part. So that's what you need to do. Okay. So I'm very sorry. I didn't find why my last Friday's recording disappeared. So I hope this video can help you understand what you need to do in this level 4. Okay, thank you. You can check this on Canvas files and Zoom level and level 4. That folder. This is the folder location. Yeah. Okay. Thank you so much. Thank you.